Assalamualaikum and greeting to everyone. My name is Wan Zubarali Dewa Muhammad Zai, and my metric number is CN220290. Today we are from Group 5 when to present my project, which is application of first order and second order linear differentiation equation. So this is my group member. First, Muhammad Syabi Haziq. Second is me, Wan Zubarali. Third is Naki Azman. Fourth is Muhammad Izwan. And lastly is Muhammad Haika. For introduction, a differential equation is an equation that contains one or more function with its derivative. The derivative of the function defines the rate of change a function at a point. A first order differential equation is a differential equation where the maximum order of a derivative is one or no order higher derivatives can appear in this equation. The general form of the ordinary differential equation of first order is given by dy over dx equal to f in bracket xy xy, where f xy is a function of x and y. So now is second order. A second order differential equation is a specific type of differential equation that consists of a derivative of a function order 2 or no order higher order derivative of the function appear in the equation. Then the general form include term like y power 2 d power 2 y over dx power 2 or y power 2 in bracket x.
Okay, next presenter is me, Muhammad Haikal bin Abdul Rahim. I want to tell about objective. First is understand the concept of differential equation, as equation contain a function and derivative and representative rate of change. Secondly is study different type of differential equation, including first and second equation. And number 3 is learn and apply the various method and a formula to solve the differential equation problem. The first thing, the method used in the calculation is first order differential equation. I use the linear equation. A linear equation is typically represent in the form of y equal to mx plus b, whereas the m is represented to source of line and b is a y-intercept. The first order differentiate is when we differentiate the equation, it equal to differentiate y equal differentiate mx plus b. Okay, the first problem that we have, a racket ball is hit straight upright with an initial velocity of 2 meters per second. The mass of racket ball is appropriate 0.0427 kg. A resistance act on the ball with force numerically equal to 0.5 v, where v is velocity of the ball at time. A, we need to find the velocity of the ball as a function of time. We have given v0 is 2, m is 0.0427 kg, and the gravity is 9.8 milli per second square, and the k is 0.5. So put it into the equation. M differentiate v dt equal to negative kv minus mg. After we substitute into the equation, and then we get the solution. We use the linear equation. which is px equal to 11.7096 v, and qx is 9.8, negative 9.8. After we integrate the the px, and then we put it back into the equation, so the final answer is v equal to negative 0.839 plus 2.8639 per exponent 11.70960. The second problem is how long does it take for the ball to reach the maximum height. We know the Vt equal to 0, and then V we change to we substitute the V equal to 0, and then put it into the equation, so we get the T is 0.104 second. And then lastly, number C is if the ball hit an initial height of meter, how high will it reach? Okay, the number C is we integrate the height, and then we substitute the equation before, and then we get the answer 1.084 meter.
Assalamualaikum and hi, I'm Izwan. I will like to present about the method that we use in this calculation. So for the first order differential equation, we use method separable equation. A separable differential equation is one that can be written in dy per ds equal to fx times dy. So in this case of a first order process, the rate of change equation is dy per ds equal to k times y. So this equation can be separated in 1 per y dy equal to k dx, and then we integrate both sides. We got ln y equal to kx plus c, where c is the constant of the integration. Next, the equation for separable equation, the city's population grows proportion to its current population. After a year, there are 1,000 residents of the city. After 4 years, there are 3,000 residents. The rate of change of the population is given by dp per dt minus kp equal to 0, where pt refers to the population at a time t. Given this, find the following: compute growth rate k, compute constancy equation to model the population growth at a time y, approximate original population at the time the city was formed. So given the information is dp per dt minus kp equal to 0, and then we consider dp per dt equal to kp, and then we got time equal to 1 year's population equal to 1,000 residents, and for 4 years population 3,000 residents. dp per dt equal to kp is equation 1. We integrate, and then we integrate both sides. We got ln p equal to kt plus c. So at 1 year's population 1,000, we put in equation 1, and t equal to 4 years, p 3,000, we put in equation 1 too. We got 6.9078 equal to k plus c for equation 2, and 8.0064 equal to 4k plus c for equation 3. And then next for equation for question A, we substitute equation 2 in equation 3. So we got k equal to 0.3362. For question B, we put k equal to 0.3362 in equation 2. So we got c equal to 6.54155. For question C, we put K and C in equation 1. So we got P 693.36 exponent 0.3362 T. We use taking and T log in this question. So for question D, we consider T equal to 0. So the T equal to 0 equal to 993 population. So that's all for the first order separable equation.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Nakib Azman bin Ahmad Zarfan. My metric number is CN220351, and now I will explain to Doctor about the second order differentiation equation, linear homogeneous differential equation. So the equation of motion for a mass spring system is m times d2x over dt2 plus k times x equal to 0. So the m represent the mass of the object attached to the spring, and the x represent the displacement of the object from its equilibrium position, and t represents time. Okay, now we proceed to the first question for second ODE. A spring with a mass of 2 kg has a natural length 0.5 meter. A force of 25.6 Newton is required to maintain its stretch to a length 0.7 meter. If the spring is stretched to a length of 0.7 meter and released with initial velocity 0, find the position of the mass at any time. So the first step, we need to find the value of K. So we use the formula of F equal to K times X, and we insert the value of force and the X. So it will become 25.6 Newton divided by 0.7 meter, and the value of K is 36.57 Newton per meter. So we insert the value of K into the formula, 2 times d2x over dt2 plus 36.57 times x equal to 0. So we assume the xt equal a times cos omega t plus b times sin omega t. So we need to find the value of omega. So the formula for the omega is equal square root k divide of m. So we insert the value of k and m, which is 36.57 over 2, and the value of omega is 4.05. And then we insert the value into the formula, which is d2x over dt2 equal negative a times omega 2 times cos omega t minus b times omega 2 power of 2 times sin omega t, and then we differentiate it. It will become negative 2a times omega 2 times cos omega t minus 2b times sin omega t plus 36.57 times a times cos omega t plus b times sin omega t equal to 0. So the coefficient of cos omega t and the coefficient of sin omega t we need to find first. So we to get the value of xt, so we use negative 2 omega power of 2 plus 36.57 equal to 0. So 2 omega power of 2 equal to 36.57, and the value of the omega is 4.28 radian per second. So the new value of xt, it will become ax cos 4.28t plus b times sin 4.28t t. So x0 equal a times cos 4.28 times 0 plus b times sine 4.28 times 0. So that's all from me. Thank you.
Assalamualaikum and good morning. My name is Muhammad Shabir Aziz Zaidi. My number metric is CN220442. Today I would like to explain about second order differentiation equation. So I using a second order fluid. A second order fluid is a fluid where the stress tensor is the sum of all tensors that can be formed from the velocity field with up to two derivatives. The equation of liquid in fluid system is written below. So next, suppose that the spring of example 1 is immersed in a fluid with damping constant. Find the position of the mass at any time. If it starts from the equilibrium position and is given a push to start with an initial velocity Pf 0.6 ms. So for the formula is d square y over dt plus 20 dp over dt plus 64t equal to 0. So next R2 R square plus 20r plus 64 equal to bracket r plus 4 bracket r plus 16 equal to 0, and R1 is negative 4 and R2 is negative 16. So next, y bracket t equal to C1 exponent negative 4t plus C2 exponent negative 16t. Next, y bracket 0 equal to 0, C1 plus C2 equal to 0. Y prime equal to y prime bracket t equal to negative 4 C1 exponent negative 4t minus 16 C2 exponent negative 16. So y prime bracket 0 equal to negative 4 C1 minus 16 C2 equal to 0.6. So lastly, since C2 equal to negative C1, this gives 12 C1 equal to 0.6, C1 equal to 0.05. Y bracket t is equal to 0.05 bracket exponent negative 4t minus exponent negative 16t. Thank you.
In a conclusion, differentiation equations are essential mathematical tools used to describe the relationship between a function and their derivative. They find application in various scientific and engineering fields, enabling us to understand and predict the behavior of dynamic systems. A first order differential equation are characterized by having the highest derivative of order 1 involve the dependent variable and independent variable and the derivative explicit. On the other hand, a second order differential equation involves a derivative of order 2 and excludes higher order or high order derivative. That's all from us. Thank you.